Howdy, students. Today we're going to talk about balancing equations. You can think of balancing equations as more like a balance, mass balance, like this scale here. If you add a little bit to one side, you have to add a little bit to the other side until they balance each other out. So let's learn why we should care about this and what this really means. So first of all, in order to do this, you have to be able to count elements accurately. So let's do some practice. Oh, look who joined us and is very interested. I can count exactly one cat. And he is made of all sorts of elements and compounds. And he decided that he wanted to come help me teach you about each of these elements. So let's do it. There is one sodium, one oxygen, and one hydrogen in sodium hydroxide. In Li2SO4, we count 2 lithiums, 1 sulfur, 4 oxygens. This gets a little trickier, though. Calcium has 3, obviously, but how many are here? Remember, you got to distribute this through. So there are 2 phosphoruses and 2 times 4, 8 oxygens. That's going to come in handy later to be able to do that. So chemical reactions. We need to think about the law of conservation of matter, which says in any reaction, matter is neither created nor destroyed. You can do things, but you cannot create or destroy matter. That doesn't happen. It's a law of nature. It's not going to happen. So how do we take that into account? No atoms can be created. No atoms can be destroyed. So really what happens is just energies are created, destroyed, or bond energies are created, destroyed, or the energies are rearranged. But that is not changing actual matter. Matter needs to stay the same. So let's check to see if matter is really conserved. So water. We know, very, very important in life, and it is formed from hydrogen and oxygen. Hydrogen and oxygen are diatomic. Mr. Brinkelhoff is how we remember that. And these two come together to form water. However, this is not a real equation, because not the right equation. We have the right amount of hydrogens here, because there's 2 that go into the reaction and 2 that come out. But oxygen, we've got 2, and that means we only got 1 here, so something's wrong. This doesn't conserve matter. Like I said, 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. So we need to balance this equation so that the number of atoms at the start equals the number of atoms at the end. So how do we do that? Why do we do that? To show how much of each reactant is needed to make a certain quantity of product. We're going from here to stoichiometry, and you're going to be able to use this. I could tell you, make me this much of this, and you would be able to react the certain amount of reactants and produce a certain amount of products if you can do this well. In order to make sure that things balance, you add coefficients, which are just multipliers for the formula, meaning we need, if you add a coefficient, it's that many times what's ever behind it. So here, CO2, we see CO2 right here. We see 1 carbon and 2 oxygens. But if we have a coefficient out front, that means this is going to multiply past everything beyond it. And this is going to multiply everything too. So again, like I said, 1 carbon. This coefficient means now we have 2 carbons. This coefficient means we have 2 bariums. But we only have 2 here. However, this 2 carries through, so now we have 4 oxygens. Well, this is 2 times 1, but don't forget this parenthesis out here is 2, so we actually have 4 oxygens here. And we also have 4 hydrogens, because 2 times 1 times 2 gives us 4. So here's some general rules for balancing. First thing you need to do is identify the reactants and the products. You're going to write the equation. You're going to go from words to the formula and predict the products as necessary if you need to. All formulas need to be correct. They need to be properly written to make sure charges within the formula are balanced. Otherwise, this doesn't work. Then you're going to count atoms. You can actually do a little bit of a shortcut and look for polyatomic ions, which you can count as one unit, and that'll save you a little bit of time. You can insert coefficients. Don't alter the formulas themselves, but insert coefficients. Don't change subscripts at all. Just balance one atom or polyatomic ion at a time. And elementals, which are AH2, O2, things that are just the elements themselves, you should save until last. That's going to help you out later when you get to some harder ones. Then check your results, and that's all you got to do. So here's an example. Generally what I recommend is writing each of the elements in the reaction underneath the reaction sign, underneath the yield sign. That way it's easy to count one side or the other. I find people when they write them over here, when they write them across, when they write them to the side, they lose this, and that's how they make mistakes. So we do that. Sodium. We're going to draw these dashes. To the left side, we're going to have the number of each over here. To the right side, we're going to have the number of each over there. So we need to see we have one sodium, 2 hydrogens, and 1 oxygen on the left side, the reactant side. On the product side, we have 1 sodium, 1 oxygen right here, but we have 1, 2, 3 hydrogens. So what do we need to do? Well, we probably need to balance out the hydrogens. They're the only thing that's off. So let's start that. What we can do is put a 2 here. That is going to make it so that we can balance the other side. A good trick is that if you see an even number on one side and an odd number on the other side, do whatever it takes to make that odd number even. So we had 1 here. We want to double this so we can get 2 oxygens and 2 hydrogens. So that gives us 4, which we're going to work on later. But again, this is a multiplier, so this means everything after it is going to need to get it as well. So this gives us 2 sodiums as well, 4 hydrogens because we have the 2 times 1 plus the 4, and then 2 oxygens. But we need to balance the other side now because we're all out of whack. So we drop another subscript in there in front of water. That means that we've got 4 hydrogens, we're balanced there. We've got 2 oxygens, we're balanced there. But we aren't quite done yet because we need to take care of the sodium. So we do that. We add our last one here. Remember, save elementals. Elementals meaning things that are all by themselves for last. We add the 2 subscript, meaning this is going to change this multiplier, and we're good to go. This, remember, is going to be the total number of each element, not what you multiply by. That's going to be the coefficient up here. Just put down here what the final number is. That way you can see on each side that we're good. Let's do another example. So let's count. We've got calcium, so we're going to write Ca dash dash. We've got silicone. Write it down again under the arrow, and we've got chlorine. Now let's check the other side, calcium, silicone, chlorine. Okay, so how many calciums do we have? Well, we have right here 2. How many silicones do we have? Well, we have just the 1. How many chlorines do we have? We have the 2. Other side. we only have one calcium. Silicone, or let's go to chloride. We've got two chlorides. Actually, check that. 2 here plus 2 here means we actually have 6 chlorides. And then silicone again, we just have 1. So we don't have to worry too much about the silicone. But remember, everything else is a little out of whack. I could change this chlorine right now, but since it's all by itself, it's an elemental. Ella for short. So we're going to save it for last. So that means let's balance our calcium first. So we've got 2 here. Let's put a coefficient out front here. Now we have 2 calciums, meaning we're good there. But again, this is going to change our number of chlorides again. So let's count. Let's see, 2 times 2 is 4 plus the 4 from before. That equals 8, which we should be all right with. Now we can balance. Again, silicone's good. Don't need to worry about the silicones, but we do need to worry about the chlorines. If we've got 8 on this side, we need to have 8 on the other side, meaning we're going to drop a 4 coefficient. And that'll take care of our chlorides. Sorry, I need to do this right. 4 times 2 is 8. This is again 2 times 2 is 4 plus the original 4 and 8. We have 8, we have 8, we have 1, we have 1, we have 2, we have 2. Yeah, that's what I was going for. Ca2Si, 4 Cl2s yields 2 CaCl2s plus SiCl4. Let's do another one. This one actually gives you the answer right away. See if you can find how we got that answer. And 3, again, see if you could find how we got that answer. Practice on your own. So that's it. Really all there is to it. There are actually, and I'm going to give you a trick in order to do combustion reactions. That's actually what these are. Combustion requires burning a fuel with oxygen. You create CO2 and you create H2O. Cellular respiration is actually a type of combustion reaction. And we're going to get into that, but this is kind of a trick that I use. I always write down CHO. And these can kind of get wonky because oftentimes you kind of have to go both ways. And probably the best way to solve this problem is to do it in this order: carbon, hydrogen, and oxygen. So let's start with figuring it out. We've got 3 carbons over here. We've got 1 over here. We've got 8 hydrogens over here. And we've got 2 hydrogens over here. And then we've got oxygen over here. And we've got oxygen over here. We've got 2 here. And we've got 2 plus 1, 3 oxygens over here. And now we see this is wonky because we can see we have an even number here and we have an odd number here. Meaning we're probably going to have to change both of them in order to make sure that we balance them out. So how do we do that? Well, I said let's first do it in this order. CHO, CHO. So let's do carbon first. We've got 3 on this side, meaning we need 3 on this side. So let's drop a 3 subscript here. That gets us to 3. Now we're good on carbon. But that changes our oxygen. Again, a common mishap is people don't take care, they don't edit as they go. So if I drop a multiplier, that is 3 carbon dioxides now that I need to take care of. So 3 times 2 gives us 6, plus the original one from H2O, plus 1 equals 7. Now, we know this isn't good, but again, we're going to wait on this. Carbon's good. Let's take care of hydrogen. 2 things that we can do here. We know, first of all, that we need to balance out the number of hydrogens over here. So we're going to do that by putting a 4 in here. Another thing that you should note and get good at is that if I have an even number over here, this other side, this odd side, is probably the side that I want to put an even number in front of here, because that's going to allow us to balance out better. So we see here 4 times 2 is 8. We're good on hydrogens. But don't forget to do the oxygen again. So then we have 3 times 2 is 6. Plus 4 times 1 is 4. And now we have 10. And this should make you happy, because we know we have a 2 over here, and we have a 10 here. We've saved our elemental for last. We followed the right order, CHO. And now, all we have to do in order to get rid of this 2 is put a 5 in here. 5 times 2 gives us 10. 3's balance out. 3 carbons, 3 carbons. H's balance out. 8 hydrogens. 4 times 2 is 8 hydrogens. And now oxygens balance out. 5 times 2 is 10. And 3 times 2, 6. Plus 4 times 1, 4. 10. We are golden. All right. So you're going to practice these. It really just takes a lot of practice, seeing different things, making the right guesses, trying, going back and forth either way until everything works out. And yeah, we're going to use this for stoichiometry, so get good at it so you understand how things are going to come together. I hope that was helpful.
Expecto Patronum!